Gonna do one more here just in case we're off Tuesday as well. So we'll see how this all works out. Um, so this one's about how temperature affects the rate. Okay, so just kind of going back, 14.2, 14.3, we were really focused more on concentration. 14.4, we were focused more on how does the concentration change over time. Okay, so really everything we've done so far has been a lot more focused on the concentration and the way that affects the rate. Now what we're going to talk about is another one of those factors that we said was a big affector of the rate, which is temperature. Okay, and any of you who did the experiment, the brief experiment with Alka-Seltzer on Friday, you would probably know that the temperature greatly affected the rate of that reaction. And that's the way that it is with most reactions. You heat it up, you speed up the motion of the particles, they're going to hit more often, they're going to react more often. Okay, and that's called the collision model. So this idea is important. They really want you to know this year. They talk a lot about the collision model in the new AP curriculum. Okay. Most reactions speed up as temperature increases. By the way, that's why we refrigerate our food. We're trying to slow down those chemical reactions that different organisms do when they eat our food. Because we want to eat our food, not we don't want something else to eat our food. So that's why we put it in the fridge for the most part. So basically, as temperature increases, the rate increases, and the rate usually has a very large effect. The temperature usually has a very large effect on the rate. Okay, now, if you would remember, when we write our rate law for a particular reaction, let's say the reaction of A going to B, which they've used that one a lot, then let's say this is a first order reaction. The rate equals K times the concentration of A. Okay, that's typical rate law. There's nothing about temperature in that rate law whatsoever. Okay, temperature is not going to change the concentration to any noticeable degree. Now the temperature might change the concentration a little bit because it changes volume just a little bit if we're doing this in a solution, but not so much that you would have this drastic increase in the reaction rate if you increase the temperature. Okay, so what must change when we change the temperature is the rate constant itself. Okay, in fact, the rate constant is only constant at one specific temperature. If you raise the temperature, then your rate constant is going to change. Okay, so that's the part of the rate law that actually gets affected when you change the temperature. I think that's what I just said. I get ahead of myself sometimes here. Yeah, the rate constant must depend on temperature. So an example of this reaction CH3NC to CH3CN, kind of looks like the same thing, doesn't it? But what's actually happening here is these two are switching places in the molecule. Okay, so that actually is a reaction because there's the breaking and reforming of covalent bonds. As the temperature goes up from 190 to 250, the rate constant goes from 2.52 times 10 to the negative fifth up to 3.16 times 10 to the negative third. Okay, that's a big jump. And the question is why, and that's answered by the collision model. Okay, so the collision model basically says in order for molecules to react, they have to collide with one another, and that makes good common sense, I think, because it's hard for molecules to react. They don't actually touch one another or come into close proximity to one another. So we're going to say they have to collide in order to react. The greater the number of collisions, the faster the rate. And the more molecules present, the greater the probability of collision, the faster the rate. Okay, so this one down at the bottom here is really our explanation for why concentration affects the rate the way that it does. The more molecules you have present, the greater probability that they're going to collide with one another, and the rate's then going to be faster. Okay. Also, the greater the number of collisions, the faster the rate. And the way that we can get more collisions is either by increasing the concentration or maybe by speeding up the particles. Okay. So the higher the temperature, the more energy is available, and that's going to make the molecules hit more quickly, and it's going to increase the rate. But the other thing that is going on here is that these things have to hit in a certain way, okay? Not all collisions are going to lead to products. So there's two things that affect whether a collision will lead to a reaction or not. One is the way that the molecule is actually turned. And I think I have an example of this on here. Okay? So if you've got this reaction of chlorine reacting with NaCl in order to make NO plus Cl2, two possible ways that these reactants can collide with one another. Okay? So the first way that they could collide, you've got the chlorine molecule coming in, and it collides with the chlorine end of the NoCl2 molecule, or the NoCl molecule. That's going to be an effective collision, because what happens there, because the two chlorines are colliding with one another, then they will make the Cl2 molecule, okay? So that's an effective collision. So if they're oriented in that way, then when they hit, they will actually react, okay? Now, an ineffective collision would be like this bottom one, where the chlorine, instead of hitting the chlorine end, it actually hits the oxygen end, and no reaction occurs. So all they do is they hit and they bounce off of one another. All right, so orientation matters. Now, the other thing that matters is that these molecules have to have a minimum amount of energy in order to react. Okay, now remember, we talked about this earlier in the year. In order to form a product, you have to break bonds in the reactants. And breaking bonds always requires energy. Okay? And so even if you look back at this example right here, right, it's going to take some energy, even though you have an effective collision here. To break this bond, it's going to take some energy. All right? So these two molecules need to have enough energy. They need to be moving with enough speed in order for those, there needs to be enough energy there for that bond to break so that the new bonds can form. And when the new bonds form, energy is released. But before the new bonds can form, the old ones have to break. And so you have to have that energy coming from somewhere. Okay? We call that energy activation energy. It's the minimum energy required to initiate a chemical reaction. So basically, it's the energy that it takes to break all those bonds in the reactants that need to be broken so that these things can then form new products. Okay? And the way that we can determine the activation energy is usually by measuring the rate of reaction at several different temperatures. Okay? So here's an example, and this one was shown earlier. But in order for this to happen, what you have to do is you have to break a couple of bonds, right? Actually, I guess you need to break one bond, and then you have to do a molecule rotation, okay? So the bond you have to break is this one right here. That's going to take some energy, okay? It's also going to take a little bit of energy to turn the molecule in the other direction, and then when this new bond forms, some energy will be given off, and that's how that works, okay? You total up the amount of energy required versus the amount of energy that is given off at the end, and that will tell you whether it's exothermic or endothermic based on the overall energy change, okay? The energy required for the twist and break is the activation energy. If you diagram this, and this is, I cannot stress how important this is. They will test you on this, all right? Because, again, this is a graph. It's a graphical representation of energy. They like this a lot, okay? So here is an example of this is kind of coming back to those potential energy diagrams we did earlier in the year, and I think I actually even showed you one like this that had a hump in it, and we didn't talk much about why the hump was there, okay? This section right here, that is the activation energy, okay? So this is the energy this thing starts at. It's the amount of energy that needs to be added to get you up to here, and then this represents the amount of energy released at the end. Now notice, we had to add less energy than the amount of energy we got out at the end, okay? So this thing ends up with a lower potential energy than what it started with, which means some of that energy must have gone out into the environment. So it's releasing energy. That's an exothermic reaction. This is going to have a negative delta H, all right? So you need to know how all of those pieces fit together when you're looking at this sort of diagram. All right, but this is a good diagram showing even, with the molecular models here, shows basically exactly what's happening as these things react. Okay? and the energy changes that occur. EA is the designation for activation energy, so you need to be familiar with that. Okay, so it says, look at the previous graph to help you answer the following question. What would the delta, well, I just answered that already, sorry. Oh, no, I didn't. What would the delta H have to be in order for the activation energy to be the same for both a forward and reverse reaction? Okay, so looking back over here, let's say that we did this reaction in reverse, because this reaction can happen in reverse, okay? Not as likely to happen in reverse, but it can. Here's where our potential energy starts, right? So this is the amount that we have to add to get us to the point where this reaction can actually occur. And this is the amount of energy that's going to be given off, okay? So this time we have to add more energy than the amount of energy that is given off the end. That would be an endothermic process. We would have to put more energy into it, okay? The only way we're going to make the delta H 0 for this reaction is if we have something that looks kind of like this, where the starting and ending potential energy are exactly the same. Those are supposed to be the same. I don't think I got those exactly level. But where the starting and ending potential energy is exactly the same, okay, that means that the amount of energy that we put into this thing to get it to happen is exactly equal to the amount of energy given off at the end, okay, and so that's going to have a delta H of 0. It's the only way you can do that, all right? Okay, moving on. Change in energy for the reaction is the difference in energy. Rate depends on, okay, rate depends on activation energy. Okay, that's important. The bigger this hump, the slower the reaction will occur, because it requires a huge amount of energy in order to get this reaction to occur in the first place, because you have to provide so much energy to break the bonds to start out with in the reactants. Now, by the way, this is how, I'm getting ahead of myself here, we'll talk about this again in a day or two, but this is how a catalyst works, okay? So a catalyst takes something that looks like this and changes it. It actually lowers the activation energy for the reaction, so it looks more like this, okay? Lower activation energy, faster rate of reaction. So that's how a catalyst actually speeds up a chemical reaction. It will lower the activation energy. Okay, so what do I want to talk about here? Minimum energy needed for, okay, so again, increasing the temperature increases the amount of molecules that have that required activation energy so that they can react, okay? So, and that's, again, that's probably pretty obvious. Higher temperature means you have more energy available for the reaction, and the more energy that's available, the more of these molecules will collide with the appropriate amount of energy so that they can react with one another, okay? So notice, at a lower temperature, which is represented by the blue line here, that's how many of your molecules, this area right here, these are the molecules that would have the energy to actually react. You increase the temperature, now you've got a higher amount of molecules that would have the energy needed to react. Okay? And it's just because they're moving faster, they're hitting each other harder, there's more energy there when those collisions happen, and so more of them are going to react. So not only are they hitting each other more often when you have a higher temperature, but more of them are hitting with the energy needed in order to actually react. So that's why temperature is such an effective rate increaser, I guess. So this is the Arrhenius equation. Okay, not my favorite version of this equation. See if I can find the better one here. There we go. Okay, and the reason, again, I like this version of the equation is because it basically looks like that one does not look like y equals mx plus b. Okay, we just have to do a little rearranging here. So to make this look like y equals mx plus b, we've got the natural log of k is equal to, and again, don't worry about the derivation of this equation, okay? But if you take the negative EA over R. You multiply that by 1 over T. Okay, then you kind of separate out the M and the X from one another, plus the natural log of A. So now you've got it in Y equals MX plus B form. Okay? So then what you have to do is if you graph the, and again, this is why we said earlier to find the activation energy, an effective way to do that is to measure the rate of the reaction at several different temperatures. Okay, so if you take the natural log of the rate constant and you graph that versus the 1 over temperature, now this is capital T, so temperature, not time, like it was in the last section, that will give you the slope of the graph, and the slope of the graph here is negative EA over R. Okay, R is the gas constant, it's 8.314. The units here are joules per mole times Kelvin, which is another unit you can have for R. So since we know R, we can solve for EA. Okay, so you know the slope, you know the R, you can solve for the EA there. All right, and I'm going to have you do this in a lab that we do for this unit, because I think it's good practice. If you don't have a lot of data, you can use a couple data points, but this is the exact part that it actually says on the AP curriculum, the new AP curriculum, that you don't really need to worry about. Okay? So let me show you where it says on the AP curriculum what you do need to worry about. It's letter C here. The Arrhenius equation can be used to summarize experiments on the temperature dependence of the rate and to interpret this dependence in terms of the activation energy needed to reach the transition state. Okay, so we looked at those activation energy graphs. We also just looked at a graph involving the Arrhenius equation. Now it says here calculations involving the Arrhenius equation are beyond the scope of this course. Okay, so what I don't think is probably going to happen, I don't think they're going to give you a graph. Well, okay, I take that back. I don't think they're going to have you do something like this. Okay, where they give you a couple of temperature points and a couple of activation energies, or not activation energies, a couple of rate constants. So they give you K1, a K2, a T1, and a T2. They tell you what the A is here, and then they ask you what's the activation energy. Okay, that's not the kind of question you're going to get here. Now, the kind of question you could potentially still get on this, you could maybe get a question where they give you a graph like this, and they ask you what's the activation energy, okay? In order to be able to figure that out, you'd have to know, okay, the slope of this line, like we just talked about, is EA, negative EA over R, okay? So the activation energy is up here. Find your slope. You know your R, you can solve for the activation energy. That's, if anything, that's the kind of calculation I think that they would probably give you. And that's how we're going to find it, figure it out on the lab as well. Okay? The following table shows the rate constants for the rearrangement of methyl isonitrile at various temperatures. So they're giving you the temperature, they're giving you the rate constant. All right? Now, they're not going to make you do this. They would give you the graph. All right? But let's say that you have this data, and this could be useful for the lab that we're going to do. Okay? So on the lab that we're going to do, if you know the temperature and you figure out the rate constant, which we should be able to do, then you can graph these things. So you can graph 1 over the temperatures here, so figure out what the inverse of each of these numbers is. And then you take the natural log of all the k values. You should be able to graph those as x and y coordinates, and you should get a straight line there. The slope of that line, again, would be negative EA over R, and you can solve for the activation energy. Okay? All right, that's it. For the temperature and rate stuff. So we'll do a lot of practice with those activation energy graphs, the ones that look like this, okay? Oh, actually, skipped over this, and I kind of like it, okay? So let's say that all 3 of these have the same frequency factors, which A is a frequency factor in that equation, which I neglected to mention, okay? A is a frequency factor. It's the measure of the probability of a favorable collision. So it's just based on how the molecules are oriented with one another How probable is it that when they hit one another that a reaction will actually occur? Okay, so they have to take that into account in the equation. So, assuming they have the same frequency factors, you should be able to look at all three of these and figure out fairly easily which one is going to be the slowest. The slowest is going to be the one with the highest activation energy. Okay, so the one with the highest activation energy is obviously the one in the middle here. And then you've got, we actually probably need to look at the numbers on these two. One is 15, that one's 15. Is that right? I think the one on the right is, I'm having trouble reading this graph actually right now, but I think that's saying it's 20 kilojoules per mole from here to here. I could be wrong about that. I may be misreading that. It's a little bit weird the way that they wrote it. But if that's 20 and this one's 15, then this would be the fastest. So this would be the slowest right here. This would be the middle. This would be the fastest. And it all just has to do with the activation energy. Okay? So those kinds of graphs, the activation energy graphs, you need to know how to read those very well. Because I guarantee you those will be on the AP exam. All right, that's it for this one. See you guys in class.